22 through 40?
38.
Huh? Okay. So 38 is just kind of a pain in the butt. I'm going to just kind of do the start of it to kind of give you an idea of what we're trying to do.
Okay.
I'm going to just start by finding the angle XYZ. So that means that we have this kind of situation, right? So I'm going to need the vector yx and the vector yz. Now you have to be really careful when you're deciding which vectors to use here, because yx and xy are different vectors. You need to make sure that the initial point of your vector is the vertex of the angle that you're solving for. So x is going to be -2 minus -8, comma, 1 minus -4, which simplifies down to 6, 5. And then yz is 5 minus a -8, comma, 7 minus a -4. And that simplifies down to 13, 11. So what I'm going to do now is use the formula for the angle between the two vectors. So when I do that, yx dot yz is going to be 6 times 13 plus 5 times 11. So that's, jeepers creepers, 78 plus 55 is 133. Is that right? I think so. Okay, and then I need the magnitude of yx, which is going to be square root of 36 plus 25, which is square root 61. And then I need the square root, or I need the magnitude of yz, which is going to be the square root of 13 squared plus 11 squared. So that's going to be 290 square root. Okay, so when I plug this in, I have cosine inverse of 133 over square root 61 times square root 290. When I type this into my calculator, of course, you want to flick the lights out on your way? Thank you. So when I do that, I get about 0.43 degrees. That's a itty-bitty tiny angle there, but okay. I think that's the case actually for this problem, is the angle sizes are absurdly small. And along the way, Michael, you'll notice I also caught 2 of the side lengths, right? So what I need to do then is find one of these other 2 angles. Let's say we find angle x. So if I do the same thing now for angle yxz, I'm going to need the angles xy, or the vectors xy, and then xz. And I would do the same thing kind of from there. So just repeating that same process. That'll get me the 3rd side length that I need. And then with 2 of the 3 angles, I can find the 3rd by just doing 180 minus the other 2.
Yeah.
So it just the same thing over again. Okay with that?
Yeah.
Just kind of a lot going on, right? All right. What else from this assignment? Colette? 36 wants the angle between V and W. So I'm just going to be using that same formula that we just used there. So we know that, v dot w is going to be the component form for vector v is this. And the component form, well, w is given in linear combination form. So I'm going to write it as a component form. So I get 7 for the dot product. Okay with that, Colette? Okay, and now I just calculator time, right? And you should get like 72.35 degrees. Is that good? Okay. Who's next? Okay, fair enough. We'll pause here. If you guys would, earlier we talked about using vectors to answer like navigational story problems, right? We remember doing that a little bit from first semester. Today we're going to talk about another vector operation called the projection. So the idea here is we'd like to be able to find a way to rewrite vectors as linear combinations. Now, one way we saw to do this was using the linear combination form and using these unit vectors I and j. Now, that's not the only way to do this, and often not really even the most, or necessarily going to give us the most insight when it comes to practical situations. What we'd really like to be able to do is to take a vector and rewrite it as a linear combination of two orthogonal vectors. You guys remember what orthogonal meant? Means that the two vectors are at a 90-degree angle. So if this is like my vector u, and this is like my vector v, what the projection of u onto v is going to be is this vector here. So the way we're going to write this is we're going to write it as the word proj with the vector v as a subscript and then the vector u after that. So what this is, the way we say this in words is this is the projection of vector u onto vector v. Everybody okay with that idea? So just all we're doing right now is describing geometrically what this projection is. So that means if I write in this vector that I call w, what is the relationship between these three vectors, u, w, and the projection of vector u onto v? Look at the way the arrows are drawn. What vector operation is going on here? So notice how these vectors are drawn head to tail. That is the same as vector addition. So what this says then is that the projection of vector v, or vector u onto v, plus vector w has to equal vector u. And if I look at our drawing here, what kind of vectors is the projection of vector u onto v and vector w? Look at the angle between them. Look at the angle between those two vectors. 90 degrees. So what can we say that, what kind of vectors can we say these are? We can say these are orthogonal. So what we've outlined here is a way to take vector u and break it up into the sum of two orthogonal vectors. Those two vectors would be the projection of u onto v and this vector w. Everybody okay with that idea? So let's look at the formula of actually how we perform this projection. So for non-zero vectors u and v, the projection of u onto v is the dot product of u and v divided by the magnitude of v squared times the vector v. What type of quantity is this fraction going to give us? Is this going to be a vector or is this going to be a scalar? This is a scalar, right? The dot product gives us a scalar, and the magnitude is a scalar. So that's a scalar. Vector v is what type of quantity? It's a vector. That was a question. So when I have scalar times vector, what operation is going on here? What do we call it when we multiply a scalar to a vector? Scalar multiplication. Thank you. So what is this projection operation doing? It's basically just scaling vector v. If we go back to our picture here for a moment that we drew at the very beginning, look at what the projection of u onto v is. It is in the same direction as vector v, right? Is its length the same as vector v? Not necessarily, probably not. It could be, but it likely wouldn't be. It is, in fact, just a rescaling of vector v. We just, in the picture, have shrunk vector v down to a new length, right? That's what happens when we do scalar multiplication. The vector either stretches or shrinks, but the direction remains the same. So what this projection is just a form of scalar multiplication. Let's do a numeric example to kind of practice doing this. All right. Let's say we want to find the projection of vector u, which is in component form 3, 1, onto vector v, which in component form is 6, -4. So this is the formula we're going to use, right? So to do this formula, I'm going to need to take the dot product of u and v. How do I take a dot product again? Yeah, it's the product of the x's plus the product of the y's. Everybody good there? How do I take a magnitude? Yeah, square root of x squared plus y squared, right? But notice that this is magnitude squared. Right? So that squared can just cancel the square root, and we're left with 52. So this works out to be just 14 over 52 times the vector 6, -4. So when I do that scalar multiplication and multiply those fractions and reduce, I get 21 over 13 and then -14 over 13. Everybody okay there? I skipped the fraction operations, but you guys should be able to handle that. Okay, so we have this answer. What if using the same vectors u and v, I asked you to write u as the sum of two orthogonal vectors, one of which is that projection of u onto v. Sure. So to do this, I'm going to use this formula that we wrote down earlier. Now we know the projection vector. We just found that in the previous step. We don't know what w is, and we know what u is. That was given to us in the problem, right? So we have this vector equation. How do you suppose I'm going to solve for vector w then? Yeah, I'm just going to subtract this projection vector from both sides. So when we make like common denominators and combine like terms, we get 18 over 13 and 27 over 13. So then I can say that u is 21 over 13 negative 14 over 13 plus 18 over 13 and positive 27 over 13. So so that would be 39 over 13. Yep, that's okay. I don't mind you checking. It happens, man. Any questions about this example that we've done? Okay. So one common example of an application that we can use these vector projections on are dealing with some force problems from physics. How many of you guys are in a physics class or have taken a physics class? Just quick show of hands. So maybe a third or so of us. Those of you that have had a physics class before, the type of story problem I'm about to write down should sound relatively familiar. So let's suppose that Kyle is going sledding on a hill. And that hill has an angle of incline of 25 degrees. Says if Kyle and his sled weigh 165 pounds, what amount of force is sliding down the hill? So, former or current physics students, does this sound like a familiar first semester physics problem? Should sound quite familiar, right? Now, these kind of force problems where things are happening at an angle, are these easy or can they get kind of terrible and difficult? I don't know if I agree with you. Oh, okay. These can get quite terrible. These sorts of problems can be quite difficult. In particular, to set up with everything going on at an angle, needing to get all the correct forces in the correct directions is often quite challenging. We can attack this same problem from a vector perspective. And I think the problem becomes considerably easier if we think about it in that regard. So there are two vectors at play here. There's the hill, and there's Kyle on the sled. Everybody agree with this? Okay. So I'm going to draw on the hill. So that's the vector h. And because we're going downhill, I'm going to draw the vector going in the downward direction. And it says the angle of incline is 25 degrees. So the angle with respect to the horizontal that the hill makes is 25. And by the alternate interior angles theorem, then this angle is also 25. Everybody agree with that? So if I talk about the direction for vector h, that's going to be 360 minus 25, or 335. Everybody okay there? Do we know anything about the length of this hill or the magnitude of this vector? We don't. That means we get to choose. What choice is the smartest choice to make here? 1. 1 is an excellent choice. So now, since I have the magnitude and direction for this vector, I can write it in component form, just like we would have done on the homework quiz. Okay, everybody's good there? Okay. I have a second vector going on, and that second vector is Kyle and the sled. The only force acting on Kyle and the sled is gravity. What direction does gravity act on any object? Straight downward. So I'm going to call this my vector K. So this is the direction for vector K. What is that angle that I've just drawn there? 270. Fantastic. And the magnitude for vector K is just the weight that's been provided, which is 165. So doing the same thing, then I have 165 cosine 270, comma 165 sine 270, which comes out to be 0, comma negative 165. Probably not surprising based on the picture we just drew, right? Okay. So the amount of force sliding down this hill is going to be my vector K projected onto my vector H, and just taking the magnitude of that. So this is the magnitude of, let's use a different color, the projection of vector K onto vector H. So let's calculate that projection vector first, and then we can come back and calculate its magnitude at the end. Everybody okay here? So I have 0 times 0.096 plus 165 times negative 0.423 over 1 squared times the vector 0.906 negative 0.423. Everybody okay with that? So that's going to give me, are we out of time? Oh my gosh. Okay. Well, you guys see what to do from here, right? We finish this up. Is here. 0.473. And then I'd like you guys to work on 41 to 46 for next time.
5.